Dear all, welcome to Learn, Unlearn and Relearn, an online program in chemistry. I'm excited to have you in the class and look forward to your contributions in the learning process. I thank God for giving me this opportunity to do something at the cause of education.
Welcome to the third lecture in Aromaticity. In the previous lectures, we have been looking into the details of the conditions and criteria for a molecule to be aromatic, and we also understood how a molecule tries to become an aromatic molecule by losing a proton or by becoming a cation or an anion. We also understood the basic criteria for aromaticity, which starts with that a molecule should be cyclic and it should have unhybridized p orbital, and these unhybridized p orbital are the result of the sp2 hybridized carbon, and the sp2 hybridized carbon are involved in bonding, and carbon has one p orbital which is unhybridized and it contains one electron. So for a molecule to be aromatic, the very basic and fundamental criteria is it should be cyclic and it should have unhybridized p orbital in a continuous system, in a continuous cyclic system. So the cyclic system should be continuous, it should not be discontinuous, and the molecule should have a planar geometry, or it should adapt to become planar. Therefore, all the lobes of pre-orbital lie in the same plane. So this is one of the important criteria for a molecule to be aromatic, where all the lobes of p orbital lying in the same plane. And finally, the molecule should fulfill Huckel's rule, and it should include 4n plus 2 pi electron. So the molecule should have a 4n plus 2 pi electron, where n can be an integer from 0 to n. Now, initially, all cyclic conjugated systems or hydrocarbons were proposed to be aromatic. However, it was found later that cyclobutadiene is so reactive that it dimerizes readily. It dimerizes readily before it could be isolated. It dimerizes readily before it could be isolated. So cyclobutadiene is highly unreactive. Highly reactive. Uh, in a similar way, cyclooctatetraene adds bromine readily. So you can readily add cyclooctatetraene, and you can see here these two structures can exist in a non-planar geometry. Okay, so both your cyclobutadiene and your cyclooctatetraene can remain in a non-planar geometry. And there is one fundamental question that always arises whenever we discuss about aromaticity. The question is, why do we say that an anti-aromatic system is less stable than a non-aromatic system, which is less stable than an aromatic system? Or in other words, if you count on the stability, of the molecule, an aromatic molecule is considered to be highly stable. Okay, so aromatic is considered to be highly stable, which is more stable than non-aromatic, and this is more stable than anti-aromatic. Okay, so if you want to get the answer for this ideology, or we would say the existence of these systems, then we have to look into the molecular orbitals, especially in benzene, to start with benzene. So we would like to understand what exactly happens there. Now when we try to construct the molecular orbitals, we can see here the molecular orbitals are always formed, the pi molecular orbitals are formed by the sidewise overlap of p orbitals. Okay, so when you have two p orbitals, okay, and these two p orbitals can overlap to form a pi molecular orbitals, and you can see the p orbitals have two lobes. So the plus and the minus sign indicates the opposite phases of the wave function, as that is psi, as described by the Schrodinger wave equation. And please remember, these two signs, that is positive and negative, they are not electrical charge. So we have to remember that in mind. It is the representation of the wave function, the phases of wave function. Now when the lobes of the p orbital overlap constructively, which means when a positive end of the lobes uh, overlap with each other, or when two negative ends of the lobe overlap with each other, a bonding molecular orbital is formed. So you can see here there are two you can see we have, let us say we have two lobes, okay, one with a positive charge and the other is a positive charge, okay, and this is what we call it as a constructive overlap. Now when positive and negative lobes overlap, the waves cancel out each other and nodes are formed, and hence we call the orbital as anti-bonding molecular orbital. Now here in this diagram we have the molecular orbitals of ethylene. Now when we say the bonding on the anti-bonding molecular orbitals of ethylene, you can see each of this carbon will be having one unhybridized p orbital, and these two p orbitals combine, okay, these two p atomic orbitals combine to form two pi molecular uh, orbitals, and among these two molecular orbitals, one happens with a constructive overlap, we call it as a pi bonding molecular orbital, and the other one happens with a destructive overlap, and we call it as a pi star anti-bonding molecular orbital. And when we try to express this molecular orbital diagram, so this is the simple molecular orbital diagram for ethylene, okay. So when we try to represent it in terms of electrons, then we have to draw uh, the energy profile diagram like this. So we will be having two bonding molecules. This is pi and this is pi star, okay. So this is pi and this is pi star, and we will fill the bonding molecular orbital with two electrons, because this has two electrons involved. This pi bond has two electrons involved. Now what are the molecular orbital rules for benzene? As you know, benzene has six p orbitals, so you can see there are six p orbitals, and therefore benzene should be forming six molecular, so six atomic orbitals in benzene. You have six atomic orbitals in benzene, So these 6 atomic orbitals combine together, okay, and they form 6 molecular orbitals. So 6 overlapping p orbitals should form 6 molecular orbitals. Among these 6, 3 will be bonding and 3 will be anti-bonding, like how we saw it in ethylene molecule. So the lowest energy molecular orbital will have all the bonding interactions. See, you can see here the difference between the arrangement of electrons. Okay, so now here this corresponds to the continuous filling up of electron, and this corresponds to the formation of molecular orbital. Okay, and we have the electrons filled up in the bonding molecular orbital. So lowest energy molecular orbital will all have bonding interaction and there will be no node. At this juncture I have to tell you, so what is a node? A node is a place where the probability of finding an electron is 0. Okay, so as energy of the molecular orbital increases, the number of nodes also increases. So there can be system symmetric. So the system is symmetric and therefore we will have 2 pairs of degenerate orbitals. So the system is symmetric, therefore we will have, so this is one pair of degenerate orbital, this is another pair of degenerate orbital. As we know, degeneracy means equal. So if we say that two orbitals are degenerate, simply means that they have equal energy. So degenerate means equal in energy. This is what we call it as degeneracy. Now, when we try to construct the energy diagram or the energy profile diagram for benzene, we have understood that in benzene there are 6 atomic orbitals. Now with these 6 atomic orbitals as transformed into 6 molecular orbitals, the system is symmetric. So there will be 2 pairs of degenerate orbitals. So when we try to arrange the lowest energy, there will be one molecular orbital at the lowest energy level and we call that as pi 1. Okay, so this is how we will construct. So benzene should have 6 molecular orbital, the count should be 6. The lowest energy molecular orbital will be pi 1. Then since the system is symmetric, so it should have 2 pairs of degenerate orbital. So this is the first pair of degenerate orbital. Then we will have a non-bonding line. So this is the separation that separates bonding and molecular orbital, and this is what is we call it as non-bonding line. Then we will have the next pair of degenerate orbital, and finally we should have the pi 6, that is the anti-bonding molecular orbital. Okay, so this becomes pi 2 and this becomes pi 3, this becomes pi 4, this becomes pi 5, and this becomes pi 6. So this is pi star 4 because it is an anti-bonding, there is pi star 5, and this is pi star 6. Now the 6 electrons are to be filled as per Hund's rule and Aufbau's rule. Okay, and so we will be filling up the electrons. So the first bonding molecular orbital will get 2 electrons, the next will get the next 2, and the next will get the next 2. Okay, we can even fill one here, and then we can come back and pair it up. So the 6 electrons fill 3 bonding pi orbitals. All bonding orbitals are filled. So this is what we call it as a closed shell because all bonding orbitals are filled, and this is considered to be an extremely stable arrangement. So when you try to construct a molecular orbital diagram and when you come across this, So when you come across that all the bonding molecular orbitals are completely filled, then the molecule is said to be extremely stable, and this extremely stable arrangement is what we call it as aromaticity. If we look into the energy diagram for cyclobutadiene, you can see by following Hund's rule, okay, so in cyclobutadiene you can see there is one bonding molecular orbital, there are two non-bonding molecular orbital. So two electrons are in separate orbitals because they are at same energy, and the most stable is filled with an electron pair. Okay. Now, if this is what happens if the cyclobutadiene molecule is planar. If the cyclobutadiene molecule is planar, then this is the possibility. If a cyclobutadiene adapts a coplanar geometry, the two of the molecular orbitals would each give a single unpaired electron, and this is considered to be very unstable. Okay, and therefore cyclobutadiene is anti-aromatic in nature. The the reason for the anti-aromaticity is due to the presence of uh, unpaired electron, which is considered to be highly unstable, and the unpaired electron is present in the non-bonding orbital or the non-bonding line. Okay, so if we try to analyze the various molecular orbital energy diagram for benzene, which is considered to be aromatic, and cyclobutadiene and cyclooctatetraene, which is considered as anti-aromatic, you can see that in benzene all the pi electrons are present in the bonding molecular orbital. So we have a closed loop of electrons, and benzene enjoys aromaticity. On the other hand, in the case of cyclobutadiene, you can see there is one electron in the non-bonding orbital. There is one more electron in the non-bonding orbital. In a similar way, in cyclooctatetraene, there is one electron in the non-bonding and one each here. The remaining 6 electrons are present in the bonding molecular orbital. Now this corresponds to the combination of single and double bonds. So when a molecule has a combination of single and double bonds, and when it is a foreign system, it will try to move away from its planar state and try to adopt a coplanarity, thereby its reactivity increases. Okay, so as far as the aromatic systems are concerned, one should always understand that in aromatic system all the bond lengths will be same. This is actually a tool to find out whether a molecule is aromatic or not. This can be a quick 1-minute quiz. So for a molecule to be aromatic, what is the experimental evidence? Okay, so one experimental evidence could be all bond lengths are same. So for any aromatic compound, all the carbon-carbon bond lengths would be same, and this is due to the delocalization and resonance. Let us try to understand the acidity of pyridinium ion. We know that pyridine is aromatic in nature because it satisfies all the condition. It is cyclic, it is planar, it has 4n plus 2 pi electrons, and it also exhibits resonance. Now it is an heterocyclic compound, and here in pyridine there is a non-bonding pair of electron. It is present in the sp2 hybridized orbital, and therefore pyridinium ion is a weak base. Now if you look into the pKb value, it is around 8.8. Now this lone pair of electron can be abstracted by a water molecule, and this lone pair can form a bond with a proton from the water molecule, and in this case the pyridine becomes pyridinium ion. So this is what exactly happens. So it is represented with the help of a beautiful pi electron diagram. Okay, so you can see the delocalized pi electrons, and this particular electron is a lone pair of electron which is present in the sp2 hybridized orbital. Okay, now when this lone pair of electron is given for the formation of a bond with a hydrogen which with H plus, nitrogen now contains a positive charge. Okay, so when nitrogen gets a positive charge, its electronegativity increases further. Okay, you can see the pyridinium ion has a pKa value of 5.2, which makes it more acidic, okay, than compared to the pyridine. And also pyridine has a pKb value of 8.8, that which means that it is a lesser base. Now let us try to compare the acidity of a protonated pyrrole. We know that in pyrrole the nitrogen is sp2 hybridized, and when this nitrogen, which contains the lone pair of electron, and we all know that this lone pair of electron is involved in resonance, and that is the reason why pyrrole is a very weak base, because in pyrrole the lone pair of electron is not available because it is involved in resonance. Therefore pyrrole is a very weak base. Now when this pyrrole is attacked by water, the electron is removed from nitrogen. Okay, and you can see now the nitrogen becomes sp3 and the aromaticity is destroyed. When the aromaticity is destroyed, you can see the jump in the pK value of protonated pyrrole. Its pK value is only 0.4, which means it is a very strong acid, because it always likes to give away H plus ion and get back its aromaticity, because you can see here this loop is missing. Now how pyrrole can get back this loop? Only when it contains the lone pair of electrons. So it can only get back its aromaticity only if it has the lone pair of electron, and that can happen only when either of these two hydrogen are removed, and that is the reason why your protonated pyrrole, which is non-aromatic, is highly acidic, and it is readily it can lose away its proton, whereas your pyrrole is aromatic. Now this pi electron density diagrams gives you a picture of the delocalization of electron density in the case of anion and cation. Now we know very well that both these molecules are aromatic. There is no doubt in that, because both these molecules obeys all the criteria, and therefore they are aromatic in nature. But even though they are aromatic in nature, you can see the potential difference in the electron distribution inside the molecular framework. In the case of anion, you can see the molecule has a dark blue outer region and a very mild core inner region, whereas in this case the density and the distribution is somewhat different. Now this is what we need to understand, that even though the molecule is aromatic, but depends on whether it is aromatic because of the presence of negative charge or aromatic because of the presence of positive charge, makes a subtle difference in the reactivity and energy profile of the molecule. Now one need to understand the molecular orbital description of aromaticity and anti-aromaticity. As far as our current understanding on the structure of benzene is based on molecular orbital theory, and as mentioned earlier, now all the 6 sp2 carbon atoms are arranged in such a way that each uses 2 of its hybridized orbital to bond to adjacent carbon atom, and the third one to bond to the 1s orbital of hydrogen. I would always recommend my students to always draw and practice the structure of benzene several times using orbitals and not using lines. So you should stop using this structural framework as you advance to the higher level of studies and higher level of thinking. You should always start drawing molecular, okay, you should always start drawing. This would be a little difficult for me here to draw. So it goes like this. So you need to draw the, okay, so I will have one more here, so I will have one more here, okay, I will have one more here. So I'm just drawing two carbons here. So when I draw two carbons, you can see this is the sp through. So I'm just giving you a shade. So what I have drawn here is the sp2 hybridized orbital. Okay, so I'm just drawing, see, I'm just drawing these two carbons, and you can see these sp2 hybridized orbitals are triangular planar, and they are oriented in a triangular planar shape, and you can see the s orbital of hydrogen can overlap and you get a sigma bond. Now the remaining p orbital, that is the unhybridized p orbital, they undergo a lateral overlap resulting in the formation of a pi bond. So this type of drawing needs to be used always. Okay, as you see this diagram, you can see we have all the atomic orbitals where each atomic orbital has one electron each, and these atomic orbitals combine together to form a pi bonding molecular orbital. And as you can see, when it becomes a pi bonding molecular orbital, you have psi1, psi2 and psi3. So all these three are bonding molecular orbitals, and you have anti-bonding molecular orbitals. Okay, the unhybridized p orbital associated with each carbon atom contain one electron and lie in the perpendicular to the plane of the ring. And according to the molecular orbital theory, these 6 p orbitals combine to form 6 molecular orbitals, 3 of which are bonding and 3 are anti-bonding. The 6 pi electrons occupy the bonding molecular orbitals. Okay, so this is your bonding molecular orbital, and which are lower in energy compared to the unhybridized p orbitals, that is atomic orbitals. The relative energies of the atomic orbitals and molecular orbitals are shown here. So you can understand that if there are any orbitals which are there in a molecule that is not involved in hybridization, they remain in this place as non-bonding orbital. Okay, so that we need to understand. This is again another way of representing the molecular orbitals in benzene. You can see this is the lowest energy orbital where the energy distribution is equivalent and it does not has a low. And as we move up, these two structures or these two depictions indicate that these two are in equal energy. Okay, they are degenerate, and also this is pi 2, therefore it will have n minus 1 node. So the number of nodes will be n minus 1, where n is the number corresponding to the wave number, and the orbital number. Okay, so here you can see that we have two degenerate orbitals. Here the number is 2, therefore it should have n minus 1 node, so it has 1 node. So this is how you can represent actually a pi molecular orbital depicting the positive and negative wave functions or the phases of the wave function. And if you look into the anti-bonding molecular orbital, it becomes pi 4 and pi 5. Okay, so these two are degenerate. Okay, these two are degenerate, and therefore it should have if I say this is the third order, okay, third order orbital, then we say then it should have 2 nodes. So the 2 nodes are depicted here. And please remember, a node is a point that or is a line that passes through two oppositely charged lobes. So whenever two oppositely charged lobes are present, then that indicates a place where a node is formed. When we look into the Frost cycle, it is one of the ways by which the aromatic molecules can be depicted, and the relative energies of pi molecular orbitals can be depicted in a planar cyclic in the planar cyclic conjugated system can be determined by a simplified approach developed by A. Frost in 1953. Now this entire process involves the following steps. The first thing is we should draw a circle. Then we need to place the ring, that is the polygon representing the compound of interest in the circle, with one of its vertices pointing down. Then each point where the polygon touches the circle represents the energy level. And then we need to place the correct number of electrons in the orbital, starting with the lowest energy orbital first, in accordance with Earn's rule. If the polygon touches the circle at a horizontal diameter, then that point should represent a non-bonding orbital, and energy level below this line indicate bonding molecular orbital, and those above are anti-bonding molecular orbital. So the steps are very simple. First we need to draw a circle, then we need to place the ring, then we need to place the correct number of electrons. Let us take an example. So what we need to do is, as I told you, the process is very simple. You have to first draw a circle. Now this is cyclobutadiene. You have to put this cyclobutadiene inside this circle in such a way that one of the vertices, touches the horizontal part of the circle. So if we try to put cyclobutadiene inside the circle, it will look like this in the circle. Now each point, so each point that touches the circle corresponds to a energy level. So each point that touches the circle is an energy level, and after drawing this we need to input the electrons. So we will first put 2 electrons here, then we will put 2 more here. So when we try to put 2 electrons here, so you will have 2 electrons here, then we will have 1 more electron here and 1 more electron here, and you can see we have electrons in the non-bonding orbital. So whenever electrons are present in a non-bonding orbital, we will say that that particular system is anti-aromatic in nature. Let us take the Frost cycle for cyclopentadienyl anion. So in a similar way, we need to draw a circle, and we need to put one of the vertices of the polygon, right? And when we try to draw this, you can see here that your bonding molecular orbitals are below the non-bonding line, and once you put in, because this molecule has 6 electrons, so you have 6 electrons. So when you try to fill up these 6 electrons, you get a closed loop of electrons, and the molecule is aromatic in nature. So that is how one can determine whether a molecule is aromatic or non-aromatic or anti-aromatic by applying the Frost cycle rule. Or we can construct a Frost cycle for every molecule, and we can check whether that particular molecule is aromatic or not. And if we construct the Frost cycle for benzene, so you try to draw benzene inside a circle, and you can see here in benzene all the 6 electrons are present in the bonding molecular orbital, and it has a closed loop structure. Therefore benzene is aromatic. And if we try to draw the Frost cycle for cycloheptatrienyl cation, see, I'm just trying to take this molecule as such, and I'm just putting it inside a circle, or I am trying to draw a circle around this molecule. So when I try to draw a circle, so please remember this non-bonding part should be the center of the circle. So please ensure that this non-bonding part should be the center of the circle. So it is actually the diameter of the circle. So you can always draw a circle, fix its diameter. Okay, you can draw. You can draw a circle. You can always draw a circle. Okay, fix its diameter, and then you insert the polygon. Okay, then you will not make any mistake. So in the case of octa 1 2 3 4 5 6 so cyclohepta trienal cation. You can see that there are 6 electrons, and all these 6 electrons are present in bonding molecular orbital, and the molecule is aromatic in nature. If we take cyclooctatetraene, the very famous tub-shaped molecule, and we know it is anti-aromatic in nature, and when we try to draw the Frost cycle for cyclooctatetraene, you can see 2 electrons are present in non-bonding orbital. Therefore, as a thumb rule, we know that if the molecule contains 2 electrons in the non-bonding orbital, then the molecule is anti-aromatic, but it chooses to be non-aromatic by adopting a tub-shaped conformation. Okay, so it chooses to be aromatic. As I told you, you can see the difference between a non-aromatic and an anti-aromatic system, as an anti-aromatic system is less reactive, whereas the non-aromatic system is less reactive, and your anti-aromatic system is more reactive. So all these things can be understood with the help of Frost cycle. So what are the points to be remembered while making predictions on aromaticity using Frost cycle? One need to always remember that aromatic compounds will always have occupied molecular orbitals completely filled, whereas anti-aromatic compounds would have incompletely filled orbitals. So anti-aromatic compounds will have incompletely filled orbitals, which means they will have 4 and pi electrons, and open shell of orbitals will be present. If an anti-aromatic system has a freedom to undergo conformational change, it will always try to become non-aromatic, and it will try to attain more energy or more stable. It will try to attain more stability by becoming non-coplanar. Okay, so by becoming non-planar, and therefore it will become non-aromatic in nature. So always remember that anti-aromatic state is less stable than the aromatic and non-aromatic. In other words, anti-aromatic is more reactive than non-aromatic and aromatic. Okay, so this is a comparison of molecular orbitals in aromatic and non-aromatic systems. Okay, thank you.